Hi, myself Saurabh Naskor, Assistant Professor of Chemistry at Gargi Memorial Institute of Technology. In my previous lecture, I discussed about Carnot engine and its efficiency. Today, I will discuss entropy. Entropy is denoted by S, and this is measure of randomness. Entropy can never be measured, but change in entropy can be measured. How? See, this is change in entropy. Del S is equal to entropy of final state minus entropy of initial state. When change in entropy is positive, then the process will be called spontaneous process. When change in entropy is negative, then the process will be called non-spontaneous process. And when change in entropy is 0, then the process will be called reversible process. And always remember, in spontaneous process, entropy must be increases. Now, entropy is a straight function, that is, does not depend on path followed, and entropy is a extensive property. Now, mathematical definition for entropy. When temperature is constant, then equation for finding out of entropy is del S is equal to del Q by T. This is change in heat, and this is temperature in absolute scale. So when temperature is constant, you should use this equation, and when temperature is not constant, then you must use this equation. So change in entropy is equal to integration of dq by T, and unit of entropy is joule mole inverse Kelvin inverse, or calorie mole inverse Kelvin inverse, or arc mole inverse Kelvin inverse. Now for non-isolated process, del S system plus del S surrounding equal to del S total. So system plus surrounding means del S total should be equal to 0, should be greater than 0 for spontaneous process. This one, del S should be positive for spontaneous process. And del S total means del S universe. See, system plus surrounding means universe. So del S universe must be greater than 0 for spontaneous process, or del S total must be greater than 0 for spontaneous process. Now in reversible process, change in entropy total will be always 0, and for irreversible process, del S should be greater than 0. Always remember, for reversible process, del S will be equal to 0. For irreversible process, del S must be greater than 0. Now for isothermal process, del S system is equal to minus dq by T, and del S surrounding is equal to plus dq by T. System means minus and surrounding means plus. So if you add these two terms, so system plus surrounding will be del S total, so will be 0. And for adiabatic process, system is all 0, surrounding is 0, also del S total is 0, because in adiabatic process this del Q is 0, so if you place 0, so del S will be always 0. This is for reversible isothermal process and adiabatic process. Now we will learn in irreversible process. See, all irreversible processes are natural process, and for spontaneous process, del S universe must be greater than 0. This one. So here del S system is equal to minus dq by T1, and del S surrounding is equal to plus dq by T2. System minus, surrounding plus. Now del S total should be system plus surrounding. So dq 1 by T2 minus 1 by T1. So T1 minus T2 by T1 minus T2 by T1 T2. This should be greater than 0, because del S universe or del S total is always greater than 0 for irreversible process. Here temperature 1 is greater than temperature T2, so T1 minus T2 is greater than 0. So this one, whole the term will be greater than 0. So del S universe should be 0 for reversible process, and del S universe is greater than 0 for irreversible process. Now we have to know some equation for finding out change in entropy in various processes. This is the equation. Del S is equal to n Cv ln T2 by T1 plus nr ln V2 by V1. Here This is number of moles, molar heat capacity at constant volume, final temperature, initial temperature, and final volume, initial volume. This is universal gas constant. Now for isothermal process, temperature is constant, so T1 should be equal to T2, so whole the term will be 0. So for isothermal process, we can write del S equal to nR ln V2 by V1, this one, or you can write nR ln P1 by P2, because P and V are inversely proportional, so we can write nR ln P1 by P2. Now for isochoric process, volume will be constant, so V1 should be equal to V2, so this term will be 0 because ln 1 will be 0, so we will write del S equal to NCV ln T2 by T1, this one. And for adiabatic process, del S is always 0 because del S equal to del Q by T, so del Q 0 means del S will be 0, adiabatic process Q is 0, so we can write del S is always 0 for adiabatic process. And for isobaric process, pressure is constant. Pressure is constant means P1 will be equal to P2, so P1 will be equal to P2 means this term will be 0, and this term 0 means this term will be 0, so this one will be 0. So we can write del S equal to NCV ln T2 by T1, this one. And here we have to write, in place of CV, we have to write CP because pressure is constant, so you have to write CP. Here volume is constant, so we have written CV. Now enthalpy change in phase change. See, here solid is changing to liquid in the process of fusion, and this process is called melting process. So here Q, this is solid is taking, if you are giving heat Q, then solid is changing to liquid. So Q is equal to here enthalpy of fusion, because the process is fusion process. So we can write change in enthalpy of fusion. So del S is, formula for del S is del Q by T. Here del Q means fusion process, so del HF. So in place of del Q, we can write del HF, and in place of temperature, we can write temperature of melting point. So T of MP. MP means melting point. This is the molar entropy of fusion. This is the formula for molar entropy of fusion. Now we will see molar entropy of vaporization. Vaporization means liquid is changes to gas, and this process is called boiling process. So in place of T MP, we have to write T BP. BP means boiling point, and in place of fusion, we have to write vaporization. So del HF, here del H, vaporization will be there. Remember, this is molar entropy of vaporization. This is equal to del H of vaporization by T of BP. BP means boiling point, and fusion means del H of fusion by temperature of melting point. Now we have a question of entropy. So that entropy of mixing of ideal gas is always greater than 0. Let's say gas 1 having moles N1 and initial pressure P1 naught, and for gas 2 moles is N2 and initial pressure is P2 naught. So after mixing, gas 1 having partial pressure P1, this will having partial pressure P1, and this will having partial pressure P2. So total pressure of mixture will be P1 plus P2 will be this one, P. Now we have a equation del S equal to R ln P1 by P2. See, this is del S equal to R ln P1 by P2. N means for n mole of gas, and R ln P2 means for 1 mole of gas. This one. Here P1 is initial pressure, this one, and P2 is final pressure, this one. So for gas 1, we can write del S1 equal to R ln, initial pressure was P1 0 and final pressure was P1 after mixing. So before mixing, this is initial pressure, and after mixing, this is final pressure. So in place of P1, we can write P1 naught, in place of P2, we can write P1, and for gas 2, del S2 is equal to R ln, this is initial pressure P2 naught, and this is final pressure P2. So net entropy change will be del S mixing will be del S1 plus del S2, this one. So this one plus this one for 1 mole, and for n mole you have to place n1 there, you have to place n2 there. Now From Dalton law of partial pressure, you know partial pressure is equal to mole fraction into total pressure. So partial pressure P1 equal to, you can write chi1. Chi1 means mole fraction of component 1 into total pressure P. And in case of P2, you can write chi2 into P. So in place of P1, I will write chi1 into P, and in place of P2, we will write chi2 into P. So let us assume P1 naught is equal to P2 naught equal to P. So this is P1, this is also, in place of P1 naught we can write P. So here we will write P. In place of P2 naught we will write P. So P and P will cancel out in both the case. So there will be N1 R ln 1 by x1 will be there, this one, and here N2 R ln 1 by x2 will be there. Now we can also write 1 by x1 means minus of N1 R ln x1 and minus of N2 R ln x2. This is, now if you take minus r common, then N1 ln x1, N2 ln x2. This is for mixing of two gas. If you mix I number of gas, then in place of chi1 you can write chi I and Ni, this one. So summation of Ni ln xi will be there. This is for 1 mole gas and this is for n mole of gas. You just put multiplied n here. So this is the final equation. Del S mixing equal to minus nr summation of chi I ln xi. Here chi1 means n1 by n1 plus n2. This is the number of moles of component 1. This is number of moles of component 1 plus number of moles of component 2. This is the mole fraction actually. Since mole fraction of gas is always less than 1, so this is always less than 1. So ln chi1 will be less than 0. Less than 0 means negative. So negative means del S mixing will be positive. So this is proved. Entropy of mixing of ideal gas is greater than 0. In my next lecture, I will discuss this part of thermodynamics and Gibbs free energy. Thank you.